Right, so this is Unit 4, Lesson 7's key on elastic potential energy. So we have on a flat, frictionless surface, a 1.43 kilogram mass is connected to a spring that has a spring constant of 75 newtons per meter. The spring is pulled 0.29 meters from its original length, and the mass is allowed to move freely. We want to know how much elastic potential energy is there at the maximum extension of the spring, and then what is the maximum speed of the mass. So here's what we know. Mass is 1.43 kilograms. Spring constant K is 75 newtons per meter. And displacement X is 0.29 meters. So far, we are all in correct units, which is nice. We don't have to do any converting. So how much elastic potential energy? Well, EPE, elastic potential energy. You could also label that as SPE if your heart desired to do spring potential energy. That would be acceptable as well. They're the same thing. Okay. But either way is fine. So that's equal to 1/2 K x squared, and 1/2 times 75 times 0.29 squared. You can't forget about the squared. That's the most easily forgotten part. People just forget to square it. So we get 3.15 joules. Then letter B wants to know what's the maximum speed. We'll define the maximum speed. That means that all of our elastic potential energy is being converted to kinetic energy. So we've got our 3.15 joules is equal to 1/2 mv squared. 1.43 times v squared. So we get 4.41 equals v squared. So v is equal to 2.1 meters per second once we do the square root. And we're skipping over number 2 because we didn't deal with the pendulum and the period part in this unit, so we're going to skip that. And then we're moving on to question 3. Okay, so a physicist loads a marble of mass 16 grams, 0.016 kilograms, just for the sake of doing conversions right away in case we end up needing it. The spring compresses 6.8 centimeters. That is 0.068 meters. The marble is launched horizontally from a height of 1 meter. 1 meter. And it lands 18.2 meters away. So we've got this spring here. It launches the marble that way. Okay. Determine the marble's launch speed and determine the spring constant. Well, the easiest way to determine the marble's launch speed is going to just be to use the Big Five. So let's write out our chart from last semester with what we know. dx, vx, and t. We know that this marble is going to be launched completely horizontally, even though I can't draw. So we're looking for vx. That's what we want to know. And then we've got v1y, v2y, a, t, and dy. Well, our dy is negative 1 meter. The height of the table is 1, and it goes down. Our acceleration is negative 9.8. Our initial velocity in the y is 0. This is a horizontally launched projectile, so a tabletop or a tabletop problem. Hey, we're going to look for time because that's the link over here. And we know that our displacement in the x is 18.2 meters. So the time is what we need in order to find velocity in the x. So we will use one of our big five equations to figure out time and then therefore the x. So we can use this one. dy equals v1y_t plus 1/2 a t squared. Initial velocity in the y is 0. So we've got -1 equals 1/2 times -9.8 t squared. So I've got -2 equals -9.8 times t squared. So 0.204 equals t squared. And so we get t to be equal to 0.452 seconds. 0.452 seconds goes on the other side. And I can use Vx equals dx over t to find my velocity in the x. So I've got 18.2 divided by 0.452. So I get my velocity in the x to be 40.27 meters per second. Okay, so then to determine the spring constant of that spring, well, we know that when it left the table, it had kinetic energy and potential energy, but what happened was the spring had elastic potential energy. It was all converted into kinetic energy. And then what determined where it landed was the kinetic energy and potential energy that it had. So we can say elastic potential energy in situation 1, which is the time it's on the table. Elastic potential energy gets converted to kinetic energy. So we've got 1/2 kx squared equals 1/2 mv squared. We are trying to find k, so 1/2 k, and then it looks like our spring compresses 0.068 meters equals 1/2, and then the mass is 0.016 kilograms times 40.27 squared. Well, the halves cancel out. So we get k times 0.004624. I'm just holding my whole number. Equals 25.95. So I'm going to divide that to solve for k. So we get k to be equal to 5,612.02 newtons per meter. So a pretty stiff spring. So question 4 says calculate and graph the energies from Q3 at these key points. Before the launch, with the spring compressed, in terms of the total energy, it's going to have all of it be spring potential energy. So the whole thing is elastic potential energy. Okay, after the marble is launched, when the spring is at equilibrium length, it's going to have a small amount of gravitational potential energy because it's on the table, which is above the ground. And then the rest of it will be kinetic energy. I did my best to make sure that those two parts would add together to make a whole, but those should be the equivalent to the total. And then the instant the marble strikes the ground, it would have completely kinetic energy. And then finally, we have reached question 5, which says a spring with a constant of 275 newtons per meter has a length of 9.5 centimeters. That's 0.095 meters. A 1.36 kilogram mass is attached to the spring. Determine the new stretched length of the spring. So this is the picture we're going with. Spring, okay, and then so that's situation equilibrium, and then we have string is more stretched out with a mass on the end. So in this situation, we know that the force of gravity down is equal to the elastic potential or the force of tension up from the spring. So we can use our spring force, our mass times gravity, is equal to our K times our displacement. So our tension would be equal to our Hooke's law equation, Fs equals Kx. Okay, so here we've got a mass of 1.36 multiplied by 9.8 equals 275 times 0.095. Not 0.095. My mistake. We're looking for that number. It's 0.095 is the equilibrium length. So we've got 13.33 equals 275x. So x is going to be equal to 0.05, or we could say 0.048 meters. So the spring is then stretched an additional 3.7 centimeters, and the mass is released. We want to determine the maximum speed of the mass at its maximum height, and we will skip that question because that goes back to a section that we did not cover and will not cover. So we're just going to do letter A. And that's all we got.